Welcome to solverfy.
So now we'll work on problem 88 from chapter 17. In this problem, we're told that two buffers are prepared by adding an equal number of moles of formic acid and sodium formate to enough water to make 1 liter of solution. Buffer A is prepared using 1 mole each of formic acid and sodium formate. Buffer B is prepared by using 0.01 mole of each. So in part A, they want us to calculate the pH of each buffer. So first we need to know the Ka for formic acid, and that is 1.8 times 10 to the minus 4. Now we can calculate the pH for each buffer using the Henderson-Hasselbalch equation. So for buffer A, we have pH is equal to the pKa, which is 3.74, and we add the log of base over acid, but it's the same 1 for both. So this here is equal to 3.74. Now for buffer B, we have different amounts of the buffer and of the base and acid from buffer A, but they're still equal to one another. It's 0.010 and 0.010, so we have the same ratio. So we actually have the same pH because it's dependent on the ratio, not on the concentration of one or the other. So for part B, it asks us which buffer will have the greater buffer capacity. And this will be the buffer that has more acid and base, which is buffer A, will have the greater buffer capacity. In part C, they ask us to calculate the change in pH for each buffer upon the addition of 1 milliliter of 1 molar HCl. So first we can calculate the moles of HCl, which we're adding here. We get moles of HCl is equal to 1 molar times 1 milliliter, or 0.001 liter, is equal to 0.001 moles. So in our Henderson-Hasselbalch equation, we can simply subtract that from the base and add it to the acid. So for buffer A, we still have pH is equal to pKa, 3.74, plus the log of base, which has now had 0.001 moles of it consumed, and the acid has 0.001 added. And when we do this calculation, it's 3.739, which is about equal to 3.4, so there's barely any change. So we say the delta pH, there's a slight change, but practically no change at all. For buffer B, we have more of a change since there's less of the species present. So this time we subtract 0.001 from 0.10, and we get 0.009, and on the bottom we have 0.011. And when we do this calculation, we get a value of 3.65, which gives a change in pH, which is equal to 0.09. So a slight change, but greater than the for buffer A. So in part D, we're asked about if we add 10 milliliters of this 1 molar HCl solution. So we calculate, again, the moles of HCl that we're adding, and it is equal to 0.010 moles. So we subtract it again from the base and add to the acid. So for buffer A, we have pH equal to 3.74 plus the log of 0.990 divided by 1.010. And that gives a value of 3.73. So this time we have a bigger change in the pH equal to 0.01. Now for buffer B, we recognize that all of our A minus, all A minus, since we're adding HCl, so all of the formate will be converted to formic acid, the weak acid, because the moles of HCl that we're adding is equal to the moles in this buffer B, moles of formate in the buffer B. So we can do a small ICE table here to show what's going to happen now that we are at the equivalence point, or we have neutralized all the formate. We only have weak acid. So that weak acid will dissociate into the base and the acid, the hydronium. So we're starting with a concentration when we add both of the moles together, we get 0.02, but then we divide by the total volume, which is now 1.01 liters, because we've added 10 milliliters to 1 liter of solution. And so this here is equal to 0.0198. Okay, and then we have nothing here, plus x minus x. So we have 0.0198 minus x and x. So we can, the Ka, as we mentioned before, is 1.8 times 10 to the minus 4, which is equal to x squared over 0.0198 minus x. This gives a value of x is equal to 1.89 times 10 to the minus 3. So we have pH equals 2.72, delta pH, change in pH equals 1.02.